Hi folks. So last time we were talking about implementing Boolean logic. We talked about drawing some pseudo circuits using our symbols there in the upper right. We talked about implementing Boolean logic or combinational logic as electronic systems using 7400 series ICs or CMOS. We talked about implementing Boolean logic using relay logic or fluidic logic. So you should be pretty good at the idea of how we can build these, but we want to talk now about some practical considerations associated with building an electronic implementation using 7400 series ICs or CMOS ICs or something like that, and how we actually wire up a circuit and what we have to watch out for. So the first thing that we want to talk about is propagation delay. And we talked about propagation delay a little bit when we talked about glitches earlier. So think about our previous example. We had buttons B1 and B2. We were pressing these buttons in order to unlock a door. And so we wrote, using De Morgan's law, we wrote our logic in terms of NAND and NOR operators. And now we want to wire up a circuit. But the thing we want to look out for is that there's this propagation delay between when you change the input on one of these gates, these logic gates, and when the output is going to change. And you saw this in your lab when you were dealing with transistors. So you change the input, and the output takes sort of a first-order response, and it takes a little bit of time. And so you can see that as the input is changing from low to high, the output is changing from high to low in this example, and we have a time delay, and that's a propagation delay. With the output going from or the input rather going from low to high. In our lab example, we talked about the delay time and the rise time, and we lumped that together as the turn on time. And then from input going from high to low, then we saw that we called that the storage and the fall time on the back end there, and that was the turn off time. So in lab, you experienced that the turn on and the turn off time might be different. And that's the same sort of thing when you look at the propagation delay associated with an IC or a logic gate. Now, when we're dealing with just combinational logic, that's maybe not such a big deal. You might have a momentary glitch, but because this is a static mapping, even though you have that momentary glitch, it's still going to work out okay after a little bit of time. The problem is going to be that when we take this the next step and we do sequential logic systems in the next segment of notes, then you're going to see that there's this memory that's introduced. And the memory that's introduced is going to respond to these propagation delays, or rather the propagation delays are going to set up some intermediate states that are going to then go into the memory, which could cause some longer-term glitches. So again, combinational logic, the glitch is short-term, and then you get the final answer. Sequential logic, it could screw things up pretty badly. So that's propagation delay. You have to be aware that it exists and plan for it. And remember that when we talked about our combinational logic and we talked about minimizing the mapping, we also talked about that we could deminimize in order to remove glitches that occurred due to propagation delay. Another thing we need to worry about is noise on the system. In a noiseless, ideal sort of thing, we've got two devices, device 1 and device 2. And so obviously if device 1 sends out a 0, then device 2 reads 0, or false, or low, depending on what you want to describe it as. If device 1 sends a 1, then obviously device 2 is going to read a 1. But the systems that we deal with are not ideal, and they're not noiseless. There is some noise, and it may be injected between these two. And so if device 1 sends a 0, and then you add in some noise, well, now device 2 might read a 0 or a 1, and you don't really know what's going to happen. And if device 1 sends a 1, and then you add in some noise, you don't know whether it's going to be a 1 or a 0. So to get around this, real implementations like TTL and CMOS include what's called a noise margin, or a buffer zone. And so this noise margin is going to allow us to connect potentially noisy systems together and have a standard that will hopefully prevent miscommunication. So let's write this in, because this graph is sometimes a little difficult to understand. And so on the output side, that's like our device 1 sending an output. And on the input side, that's like our device 2 receiving that signal from device 1. So we're going from device 1 to device 2. And so then device 1 is going to send a high, a 1. And so that's going to correspond to a voltage somewhere between 2.5 volts and 5 volts. And device 2 is going to say, well, okay, you sent me a signal, and it was a high plus some noise, so I'm going to accept anything between 2 volts and 5.5 volts as a high. And so what that means is that if, in sort of a worst case for this particular example, if device 1 sends 2 volts, and then we get a noise of a negative half a volt. Sorry, I screwed that up. If device 1 sends 2.5 volts, and we get a noise of a negative half a volt, well then device 2 is going to read 2.0 volts, which is still going to count as a high. Likewise, if device 1 sends 5 volts, and we add our worst case half a volt noise, then device 2 is going to read 5.5 volts, which is still a high. And so if we know the maximum noise that we expect, and we build that into our standards such that the output is going to be have that much noise on either side that the input will still read as acceptable, well then we can always communicate in a noisy environment. And you can do the same sort of thing at the low. So the low, the output is going to be somewhere between 0 and half a volt. And then the input is going to accept anything between about negative half a volt and 3/4 of a volt as a valid low. And so that gap in there, that half a volt gap, is what we call the noise margin or the buffer zone. So for a particular type of IC, for a particular standard, we choose a noise margin that's appropriate. And so here's some examples for the 7400 series TTL chips. The low noise margin is 0.4 volts, and the high noise margin is 0.4 volts. But this high-speed CMOS is going to use a low of 0.9 and a high of 1.4. So on the high end, there's going to be a 1.4 volt buffer on either side of the output that'll still be acceptable on the input of the next device. So now we're communicating, and we're communicating in the presence of noise. So we're accepting that there could be a non-ideal system. There's going to be a non-ideal system when we wire things up. Another non-ideal sort of thing we have to worry about is fan in and fan out. So this is going to be related to power dissipation, essentially, and how much power we can push through these things. So fan in is the maximum number of inputs that a logic gate can have, and fan out is the maximum number of gate inputs that a gate output can drive. And so what happens here is that we've got this current limit that's based on power dissipation. And so if we know what our current limit is, and we know what kind of current we're expecting on the inputs, well then that tells us how many inputs our output can drive. So typically a TTL device has a fan out of 10, so you can drive 10 other devices before the current is reaching a limit, and the corresponding voltage levels are shifting a little bit, and now it's going to be out of spec and not going to be recognizable. So how does that work? Well, if we've got 2 devices here, this is, see if I got my labels here. This dash line represents our IC, and then outside the dash line is our external sort of thing. So if we've got our V plus on the outside, and we are allowing current to flow from our V plus through a resistor, through the open collector of our logic device, and then down to ground, then we call this sinking an output. So we're providing a path to ground. If instead we allow current to flow from VCC through a resistor inside our device, outside our device through a resistor to ground, that's called sourcing an output. So that's providing a path from a voltage source. So sinking the output, we're providing a path to ground inside the device. Sourcing the output, we're providing a path from the voltage source. So What's going to be the limit? Well, the limit is going to depend on those internal components. Notice that in the sinking the output case, the current is going through the transistor, versus in the sourcing the output case, the current is going through the internal resistor. And so, as you would expect, current going through that resistor is probably going to be a less onerous constraint than current going through the transistor. Current going through the transistor, we want to keep relatively small. Current going through that resistor, we're probably fine for a relatively high current. And so you can see that we've got different capacities for sinking versus sourcing because of where the current's going, what devices is being involved. Here's our same sort of case. Now we've got the devices, the thing on the right, the shaded line, sorry, not the shaded line, the dashed line around the devices on the right. And in this case, we've got this transistor, and so we're talking about input. And so in sourcing an input, we're providing a path from the voltage source, versus sinking the input, we're providing a path to ground. I think the same sort of thing. The sinking is going to ground, the sourcing is coming from the input, but you can see that again, the current flow is going through different parts of our device enclosed in the dashed lines. Now, sinking and sourcing, it's device specific. It's going to depend on what you're using, but you can see it in your spec sheet, and this is the same sort of spec sheet I showed you before. That's a variety of 7400 series devices, and what I want you to see here is that I've got this high level input current and high level output current. So high level when things are going on, and on the input current, that's the input sink, and on the output source, or output current, that's the output source. And you can see that these are related by a factor of about 10. And so that's where we get that fan out of 10, that a 7400 series logic chip can feed 10 other devices, because it sources 10 times as much as it sinks, so it can feed 10 other chips before things get out of whack. So there you go, sourcing versus sinking. What happens if you screw up and you use more than the rated fan out? Well, in the low state, your output voltage is going to increase. In the high state, the output voltage could decrease, which means that with your noise margin, you could be out of whack and you're now getting the wrong sort of signal. Your propagation delay can increase. The rise and fall time can increase, and now everything's just sort of out of whack. You're not getting what you're expecting from your spec sheet. Your voltage levels are now potentially beyond your normal scale, and so you're potentially having misreads in terms of data. You're potentially slowing down things, which could lead to propagation delays that are going to cause glitches. So it's just a bad thing. Don't exceed the fan out, which I don't expect us to do in this class, but certainly keep an eye on the fan out. For TTL, no more than 10 devices. Another power-related thing that we need to worry about is our decoupling capacitors. I mentioned this in the previous set of notes. We need to have a little bit of local power to meet the transient needs of the IC. This is sort of similar to your need for a capacitor in your AC unit to give a little kickstart to that fan. There's a transient need for additional power. And so as these are going, they're switching, there's that need for transient power. And so we use a decoupling capacitor, typically between 0.01 and 0.1 microfarads, which, that's why we've got a bunch of those in the lab. And they go between the 5-volt and the ground supply, and you want to put them right next to the VCC for the chip. And each chip is going to have its own, and you're going to put it right by the chip. And that way, each chip is getting its own transient power supply, and life goes on, and things are good. So try to put it as close to the chip as possible, one per chip. Notice that there's all these additional inputs that we're not using on these chips. In this case, though, the gates that we're using, the one inverter and the gate here, we've got all of the gate inputs are used. But what happens if you have additional inputs that you're not using? So for instance, I've got a logic gate and I've got 4 inputs, but I'm only going to use the first 3. And so the fourth one is just sort of hanging out. What do I do? Well, it's going to act like an antenna, just like the switching case that we considered in lab. And so if you've got this extra input that's just hanging out, don't just let it hang out. That's bad. That's a floating input. So you want to either force it to high or force it to low, depending on which way you want to go with it, depending on what kind of logic signal you want it to have. But if you want to force it low, just connect it to the ground. If you want to force it high, you can either connect it to VCC if you're using CMOS, or use a 1K resistor if you're using TTL. And that way you're going to force it to take either a high or low and not allow it to float, not allow it to change, and that way it won't screw with the rest of your signal. So let's assume we're using TTL. Let's put it through our 1K resistor, and now it's forced to high, and we're not going to have a floating input. Don't allow inputs to float. On the output side, you might have an open collector. This is something we've talked about. This is a gate output that's got just a collector hanging out from the transistor on the output. There's no pull-up resistor out there, and so we might want to add a pull-up resistor. So what's it going to look like? Well, you might see on the circuit diagram, you might see one of these little things, a diamond with a line on it, a diamond with a line below it. The line on the top means it's an open collector. The line on the bottom means it's an open emitter. This is open collector. This is open emitter. And so we might add this external resistor as a pull-up. So thinking about this, well, how does this work? This means that we have to worry about the current flow again, because the current flow through that resistor is going to determine the current flow through the transistor, and so we want to make sure that we are considering what the maximum current through that transistor is going to be. So what's the maximum current flow through Q3? Well, that's going to be dependent on the current sink of the device. So you need to know, again, your spec sheet, what's the current sink? Choose a resistor that's going to be appropriate so you don't exceed that. And also that particular one may be a different rating than the rest of the chip, so be very careful to look at your spec sheet and see what the current sink is for that particular transistor. So here's some examples of how you might use that. You might have a relay on the outside there, so when that Q3 switches, it's going to energize that relay coil. Notice that this is an inductive device, so I have a flyback diode, flyback or kickback or freewheeling, whatever you want to call it, a protection diode to protect my circuit. I could have an LED that's going to turn on and off depending on the device, and so I've wired it in. In this case, it's just going to use fewer components than if I did something different. So there are some uses for this. Another one that you might like is that if we've got open collector outputs, we might wire a bunch of them together. Notice that the star in this case means that we've got open collector. We might wire a bunch of them together, and that will give us one big logic signal. And so why would you use this wired logic? Well, what if you have some sort of emergency shutoff? Well, an emergency shutoff on any one of these is going to trigger, right? So this could be some sort of general interrupt that's important, and so it might be easier to wire them together like this instead of using a different type of logic gate. So in this case, what will happen is this will output low if any of these is low. A, B, C, D, E, or F is low. So in this case, if you hit that switch, one of these goes low, then the whole thing goes low, and now you've got a trigger for the entire system. Let's see. So you could also have a bus connection. It's kind of the same idea that if you've got this bus connection, then you've got this wire that's going to contain all of that. That's going to connect to all of these, and so any of these switches could control what's on the bus. And so it's the same idea with the wired logic, is that we're going to allow any of these to tell it what's on the bus. So if you're using something like a bus, sometimes it's useful to use what's called three-state output. So in three-state output, what we have is an output switch that allows us to disconnect So it's not just high, it's not just low, it might also be disconnected. And so you might see this listed as an enable. You might see this called tri-state logic. But what it is you're going to have this disconnect state, and in the disconnect state, essentially your output of this device is not connected to the bus line. So if you have a bunch of different devices connected to the same bus line, they're all talking on the same bus line, you can use the enable to decide who gets to talk. You only enable one device at a time, and then the rest of them have to just sit there and be disconnected. So now you've got a more complicated circuit because you need to worry about your enable line, but it does give you the ability to utilize a common bus line, which in a lot of cases works pretty well. So if you think about how your computer works, well, it's going to use a bus. We're not going to talk about the computer systems a heck of a lot, but sorry, when I say computer systems, now I'm thinking about a CPU and like a desktop processor. In that case, we're not going to talk about that a lot, but they do use a bus where a lot of different devices can talk, and the way you do that is by enabling who's able to talk and who's able to listen. So this allows you to be more noise immune. It can be faster than your open collectors. It's very useful a lot of times. So you may see some additional terminology. You might see that a particular chip has a CS, a chip select port, versus an output enable port. An output enable port is what I'm talking about here in terms of 3-state, where the output is either high, low, or completely disconnected. A chip select is usually more about turning the chip on or off. The chip is active or inactive. Another type of device that you might run into is called a Schmitt trigger. So in a Schmitt trigger, what we're looking at is what happens when you have a noisy signal and it's crossing a trigger point, kind of like when we're triggering our oscilloscopes. When we've got a noisy signal going back and forth past this trigger point, then what you see on the output is that, in this case, it goes high, it goes low, it goes high, it goes low. And so there's this back and forth, this bouncing phenomena on the output. It is going 0 to 1, low to high, 0 to 5 volts, whatever you want to use as your spec here, but it's bouncing back and forth very quickly. And so if we were triggering if we were using that as an input for our combinational logic, we would end up with combinational logic that's bouncing all over the place and could be behaving very badly when you consider propagation delays and if you add in sequential logic. So a Schmitt trigger is useful to add hysteresis. And so hysteresis is something like this, where you've got this gap in these transitions. So in this case, the input is going from 0 up to 5 volts and then beyond. And then it goes from 5 volts down to 0. And so what happens is that the output isn't going to transition until the input gets on a rising edge to 5 volts. And on the falling edge, it's not going to transition until it gets down to 4.5 volts. And so you've built in this gap. And so when you build in that gap, it means that this back and forthness is going to an extent, be wiped out, and you should debounce it. So here's what it looks like. As our noisy signal is going up, it passes the low threshold, and so it's going to the output is going to stay at its original signal. And eventually it passes the high threshold, and the output responds. And so the noisy signal now is working around the high threshold, but it's not going to change the output at all. And eventually that noisy signal is going to get down below the low threshold, and the output changes. And then eventually the noisy signal gets back up to the high threshold, and it changes. And so you can see that by building in that gap, the noise does not affect things as badly. Now, sure, if we had some really big noise on our signal, we would still be transitioning back and forth and bouncing. But if we know what the noise is, we can choose an appropriate gap between the thresholds such that we are only changing occasionally, which should help our logic. So this could be called a latch. It's a on-off sort of thing. And it might look something like this in terms of a symbol. That's a terrible drawing. Let's try that again. We got our triangle, and we got our hysteresis built in there in the triangle. So that's our little hysteresis showing. So when we put all this stuff together, we get these integrated circuit packages. The dual inline package is what we're using in class. It's got pins on one side, it's got pins on the other side, and they have a gap between them, and the gap between them means you can put them into a breadboard nicely. More useful for making a larger device is the surface mount packages. Notice in this case the legs sit flat on the surface. That's the surface mount. And so if there's a pad there, they'll sit flat on that. That's difficult to solder. It's difficult to deal with in lab, but it's how you would assemble a much larger circuit board. What goes inside it? Well, it kind of depends on the sizing that you're talking about. I've got some numbers here, and I would just say that these numbers are very old at this point. So if you're talking about what's inside one of these chips, we used to say small-scale integration would be somewhere between 1 and 20 gates, which would generally be our dual inline package. That'd be our 7400 series stuff. On the very large size, you can see I've got 500,000 transistors here. That's a terrible number. If you look at the Intel i7 series desktop processors, the one that I pulled had 731 million transistors. 731 million. So that's your very large scale anymore, is in the hundreds of millions of transistors. So what we're dealing with in terms of these small logic chips, these are tiny little things. The dual inline package is just to give you a place to connect to it. The actual thing is very small. But on the big side, we've got huge layouts, which is why when you look at yields associated with things like the i7 microprocessors, you have to have very pure silicon so that you don't get any impurities that are going to destroy your functionality of the thing that you're doing. So somewhere in the middle, between these two ends, is what we call programmable logic devices. And so they would be somewhere in here between your medium scale and your large scale. That would be your programmable logic devices. So your PLDs, your programmable logic devices, are something that are going to take some logic circuits and they're going to jam them together and they're going to be easy to program. So they're fast because they're not running like a microcontroller. A microcontroller is running a set of instructions. It's running in series. PLDs are actually like logic circuits where they're running in parallel and they're bounded by propagation delay, not based on the cycle times. So they can be very fast and they can be very configurable as long as you understand that you have to fit everything within the available amount of logic that's on it. We actually used to teach this class using PLDs, and they're quite easy to deal with. The cost got prohibitive, and frankly, the Arduinos are capable of a lot more these days. So if you were laying these out on a breadboard, you might make something like this using just 7400 ICs, and this would work very well. Although that's a lot of wires, it's a lot of debugging, which is kind of difficult. But if you're like most students I've met, you'd actually make this one, and that's almost impossible to debug. So PLDs provide a nice replacement for this, that they have the same sort of functions that your standard logic devices have, but they're like an Arduino, that they're easy to program, easy to reuse. Not quite like an Arduino. In the ones we had before were some lattice ones that were you had to have a specialized programmer that was considerably more expensive than a USB cable, and they had a limited number of reprograms. But still, a lot easier than that spaghetti wiring. Very similar to what you would use with an Arduino, but much faster for implementation of just combinational logic. So what's it look like on the inside? It looks something like this. It's got some spots for you to hook up some inputs. It's got some inversion of each of the inputs in case you happen to need it. It's got some logic gates. And then it's got these little spots right here for you to make connections. For you to say, okay, in this particular circuit, I want to make a jumper here, and here, and here, and here. And then the output of that means that this output Y would be based on the jumpers and the inputs. And so you can see that in this case, I'm not using every input to my logic gates, and that's fine. I'm using the logic gate itself, and there might be additional copies of this throughout the PLD that maybe I'm not using, so there might be some wasted space. But still, I'm only using the portion of it that I need. How do I do that? In reality, well, it's going to look slightly different, but we're still going to have the same sort of thing. That I'm going to have inputs and inverters. I'm going to have some connections, and the connections are going to vary by device. There's going to be some AND matrix, and there's going to be an OR matrix. So put it together, something like this. There's the AND matrix, there's the OR matrix. There might be sequential logic for what we're doing right now, no. But notice that everything is based on sum of products in this case, and then we've got some inverters on the output. So how do you make those connections? Well, you could make them one time with fuses. You just burn out the ones that you don't want. You could use anti-fuses, like CMOS. You could erase with UV light. You could erase electrically. You could use this SRAM. Notice that the SRAM, though, you lose everything in power down, which isn't quite as nice. So there's a lot of different ways. They are erasable, they are reprogrammable within limits, or you could use the one-time uses. And in this case, they start to look a little bit like a newer device called and I just lost the name, FPGA, there we go. Field Programmable Gate Arrays. A similar device, but a little bit different in terms of implementation. And so if you think about these two, well, I guess I'll talk to you about the ASICs and the FPGAs first. ASICs compared to a programmable logic device, an ASIC is an application-specific IC. That's where you've designed specific to the task that you are dealing with. So a PLD is more of a general structure that you could set these fuses within it in order to adapt it to your particular design. An ASIC would be if you designed specifically for the one thing that you needed, which means that it's very efficient for that one task, but it means that it's expensive because I hope you're making thousands. An FPGA is, instead of using logic gates, is going to use lookup tables. And it's we have some examples. So if you take the next class in this sequence, 6183, we'll use the National Instruments C-RIO, or now the MyRIO platform, which contains FPGAs. It's a different way of implementing, but it's the same sort of idea that you're going to set the ones that you need, and the rest of them that you don't need are going to be wasted for that application. But it is reprogrammable, and it's very quickly reprogrammable, which is great. So let's look at a couple of different ways to set those fuses. So in a programmable array logic, which is an older technology, this is sum of products, and this is a particular trade name. So we've got that same sort of structure we had before. We have our inputs, we have our inverters. Here's some logic gates here. And so what we're going to do is we're going to write out our sum of product realization of our equation that we want. So in this case, Z0 is going to be x1 and x3, or x0 and x2. So I'm just going to mark those spots to fill in a junction here. And so there we go. I've worked out a Z0 that's going to have in the blue x1 and x3, or x0 and x2. And in Z1, I'll do the same sort of thing. So I'll work out some nodes here to join some lines together. And that didn't come out the right color. I apologize. And so notice that what happens here is that this portion and this portion are wasted. These two are wasted, which for the equation that we've got here, that's actually not bad utilization, but it is lost space that I can't use. A slightly more efficient one is I could use programmable logic array. And again, this is just a slightly different name, slightly different implementation. In this case, I've got a programmable OR array. So the AND is still programmable, the OR is now programmable. So if I put in my x1, x3, x2, x0, now I'm going to wire up my ORs. And then Z1, I'll do the same thing. And so in this case, I have used this space, and this space is still available. And unlike the previous case, it is available completely. I can put something in it. In the previous case, it was wasted. I couldn't do anything with it. This is more efficient because I'm making additional connections. But you know, that means that you're making more connections. So it's in addition to being more efficient, it's also more difficult to deal with. So I can fit in this additional one. In this case, I chose to do an additional one using connections I'd previously made. So there's no reason that I couldn't make Z2 here work off of those previous blue and pink connections. I could also use read-only memory. In this case, I might set up read-only memory to have a 2 input, 4 output truth table. And so in this case, I've got addresses on the input and I've got data on the output. And so the address pulls out one set of data, which is basically the same thing as setting up a combinational logic circuit that's going to produce this same truth table. But I might record it in ROM instead of recording it as a combinational logic circuit. Erasable PLDs, those are the ones that we can reprogram them, typically a limited number of times, but still we can reprogram them. So we can use this logic as the core of our device and then add other stuff to it, kind of like our FPGAs. And then typically what will happen is this array logic is going to be in these macro cells, and then we'll reproduce this macro cell multiple times, which aids the programming, because if we know how to program one of those macro cells, certainly we can program all of them. And so for lots of small equations, we can make efficient use. If we had several really big equations, it might be a little more difficult. The problem here is that it's going to be programmed using something called hardware description language, HDL or VHDL, which is not necessarily a widely known skill. And anymore, when you look at FPGAs and microprocessors, there's sort of this blurring of all these together, which is part of why we went away from EPLDs in terms of this class. But it is something that's out there still. It's useful. It's going to implement your logic. It's going to implement it very fast. It's going to implement it relatively efficiently, and it's reprogrammable in the field, which is great. So there you go. Hopefully, you've got a taste of how to implement a practical Boolean logic or combinational logic circuit. Hopefully you can do this in lab. You're going to have to do this in lab. And our next topic is going to be sequential logic, where we take our combinational logic and we add memory, and that will be the building block of a finite state machine, which you will use to program your logic behind your semester-long project.